So in this video, we're looking at CC10, which is electrolysis. This is a paper 1 topic, so it will come up on paper 1 only. So if we just look at the word electrolysis, it's composed of the word electro and the word lysis. And the word electro refers to electricity, and the word lysis means split. So what electrolysis literally means is that you're going to use electricity to split something up. Now, in terms of what you are splitting up, it's going to be an ionic compound. So electrolysis is a technique where you use electricity to split up an ionic compound. So if we think of ionic compounds are made of a metal and a non-metal. So if you take an ionic compound and you use electrolysis, you will get the metal and the non-metal back. So if we look at an example, sodium chloride is an ionic compound. It's made of a metal, sodium, and a non-metal chlorine. If I use electrolysis on sodium chloride, I will split sodium chloride back into that metal, sodium, and that non-metal, chlorine. And notice when I'm writing the name of the non-metal, I'm writing it as it appears on the periodic table. So instead of writing chloride, I'm writing chlorine. That's the name of my non-metal. If we look at another example, lithium bromide. Again, it's an ionic compound because it's made of a metal, lithium, and a non-metal bromine. And if I use electrolysis on lithium bromide, I would split that up into the metal lithium and the non-metal bromine. Again, that's bromine, not bromide. The last one, potassium iodide, that would split into the metal, potassium, and the non-metal iodine. Okay, you're always writing the names of the elements exactly as they appear on the periodic table. So, as I mentioned, you're using electricity to split up ionic compounds. And for this technique to work, your ionic compounds must be able to conduct electricity. In general, a substance will only conduct electricity if it has charged particles that can move freely. If we think of ionic compounds, they do have charged particles. Ionic compounds are made of ions. Ions are charged particles, so they do have charged particles. But can those ions move freely? Well, that will depend on what state the ionic compound is in. If your ionic compound is solid, particles in a solid can only vibrate. They cannot move freely. So even though you've got those charged particles, you've got the ions, if your ionic compound is solid, those ions can only vibrate, so cannot conduct electricity. However, if you take your ionic compound and you turn it into a liquid, then you still have your ions, so you still have your charged particles, and in a liquid, the particles can move freely. There are two ways that you can get an ionic compound into liquid form. You can either melt the solid or you can dissolve the solid. Okay? Either way will get the ionic compound into liquid form, and when it is in liquid form, those ions that it has will be free to move and it will be able to conduct electricity. If you melt a solid, we refer to this as molten, or we say the ionic compound is liquid. So if you've melted a solid, we say the ionic compound is molten or liquid, and it would have the state symbol L, a lowercase l. If you take that solid and you dissolve it, then we would describe it as being aqueous, or you can say in solution, and you would use the state symbol AQ. So two different ways to take your ionic compound and get it into liquid form. Of the two, dissolving that solid is going to be easier. The reason melting the solid will be difficult is ionic compounds have a high melting point. So if you remember back to structure and bonding, we learned that ionic compounds are made of oppositely charged ions and that there is a strong electrostatic attraction between those oppositely charged ions that requires a lot of energy to break. So melting ionic compounds is going to be expensive because it will require very high temperatures. Dissolving an ionic compound will be a lot cheaper and a lot quicker. However, in the next video, you will see that it is not without its problems. However, for now, we'll just focus on the fact that you just need to get your ionic compound into liquid form, you melt it, or you dissolve it in order to do that. Ionic compounds that are able to conduct electricity, so ionic compounds that are in liquid or aqueous form, are called electrolytes. So if I give you an example here, I'm going to give you 3 ionic compounds, and I'm going to write the state symbol after them. And then we'll see which are electrolytes. Okay, so I'll give you 3 ionic compounds. The first one is a solid, so S stands for solid. If it is an ionic compound in solid form, it is not going to conduct electricity because it does not have free moving ions in the solid. Those particles can only vibrate in a solid. Therefore, NaCl solid is not an electrolyte. If I have potassium bromide in liquid form, potassium bromide is ionic, so it does have ions. And if it's in liquid form, those ions will be free moving. It will conduct electricity. It is an electrolyte. Sodium iodide, this is aqueous. So aqueous means I've dissolved it in water. That's putting it into liquid form. So those ions will be free moving, and sodium iodide aqueous will conduct electricity. So potassium bromide liquid, sodium iodide aqueous, they would both be electrolytes. Sodium chloride solid would not be an electrolyte. Those ions are not free moving. Sodium chloride solid would not conduct electricity. So as already mentioned, electrolysis relies on electricity to split up an ionic compound, and that electricity is going to be supplied by a battery. So I'm just going to draw out a diagram, and to represent my battery, I'm going to use a plus and a minus. So this is just going to represent my battery, and this battery is going to supply the electricity. But I need to get the electricity from the battery into my ionic compound. So I'm going to draw a beaker. And into my beaker, I'm going to place my ionic compound. Now remember that ionic compound has to be in liquid form because it does not conduct electricity in solid form. So I'm going to pretend that my ionic compound is sodium chloride, NaCl. I'm going to say that it's NaCl in liquid form, so I'm going to use a lowercase l. And because sodium chloride as a liquid conducts electricity, then I can describe sodium chloride as being an electrolyte. Okay, I need my electricity to get from the battery into my ionic compound. And for this to happen, I'm going to use substances called electrodes. I'm going to connect one electrode to the positive end of the battery. And I'm going to connect another electrode to the negative end of the battery. Okay, so these substances that I connect to the battery and then place into my ionic compound, these substances are called electrodes. And there are a few different materials that you can use as electrodes, but all of these materials must have the following 3 properties. Okay, so to be a substance that is suitable for use as an electrode, that substance must be able to conduct electricity. Okay, so remember, conducting electricity just means let electricity pass through. You've got electricity in your battery. You need that electricity to leave the battery, pass through the electrode and into the ionic compound. If your electrode didn't let electricity pass through, then the electricity would not be able to pass from the battery into the ionic compound, and we need the electricity to pass into the ionic compound to split the ionic compound up. So that's a key criteria. Electrodes must be able to conduct electricity. They must also have high melting points. You want your electrodes to be solids, and you want them to stay solids even during the experiment when things get a bit hotter. So they need to have high melting points. And the other criteria is they must be inert. And inert just means unreactive. And the reason they must be unreactive is you're placing them into an ionic compound that has metals and non-metal ions in there, and you don't want your ionic compound to be reacting with your electrode. So these are the three criteria that a substance must meet in order to be suitable as an electrode. And the substances that we typically use as an electrodes, graphite would be one, and platinum would be another. So we came across graphite when we studied structure and bonding. Graphite does conduct electricity because it's got delocalized electrons. So it's got charged particles that can move freely, so it conducts electricity. Graphite is giant covalent and has a very high melting point, and graphite is also inert. So graphite meets all of these criteria, and we use graphite as an electrode. Platinum is a metal. Okay, because it's a metal, it can conduct electricity because again, it's got delocalized electrons. Because it's a metal, it has a high melting point. Because it's this particular metal, platinum, is inert. It is unreactive, although a lot of metals are not. Okay, so there are two substances that are typically used as an electrode. You connect your electrodes to the battery, and the electricity passes from the battery through the electrode and into your ionic compound. The substance or the electrode that you connect to the positive side of the battery is called the anode. And the electrode that you connect to the negative side of the battery is called the cathode. And in order to remember that, I always use PANIC, P-A-N-I-C, which stands for positive anode and negative is cathode. So the positive electrode is called the anode, the negative electrode is called the cathode. Okay, so it's just a way to avoid saying positive electrode and negative electrode all of the time. Instead of saying positive electrode, you'll just say anode. Instead of saying negative electrode, you will just say cathode. Final thing that I just need to mention on this is, in terms of the type of electricity used, you've got two different types of current. You've got DC, direct current, and AC, alternating current. In electrolysis, we use DC. We use direct current doing electrolysis. I'm now going to get you to do a few questions, which I'm going to put here under the visualizing. Okay, section A. So at this point, you need to press pause and you need to practice answering these questions. Press pause, and when you are ready to see the answer, press play again, but please do have a go at these questions yourself. Make sure you understand them. Okay, so I've got the answers here. When I'm asking for the type of compound, that will just be ionic compounds. Type of current, DC, as opposed to AC, so direct current. The state, liquid or aqueous, or you could say molten instead of liquid. State symbols, aqueous is AQ, molten is L, so lowercase l. For a solution, solution and aqueous mean the same thing, so they both have the state symbol AQ. Why must magnesium chloride be aqueous and molten? Okay, you can't just say so it can conduct electricity. You would have to explain why it conducts electricity. Okay, so when it's aqueous or molten, the ions are free to move. So the ions must be free to move to carry current, and that's why it must be aqueous or molten. Why does solid sodium chloride not conduct electricity, and what could you do to make it conduct? So in a solid, the ions cannot move freely and therefore cannot carry current. You need to mention ions. It's not just enough to say charged particles. You have to have ions in your answer. Also, don't just say ions are not free. Say they cannot move freely. Don't say they cannot move at all, because they do vibrate. So be clear with your terminology. Ions cannot move freely and therefore they cannot carry current. To change this, to get those ions moving freely, you could melt or dissolve the ionic compound. That would get it into liquid form. And in liquid form, those ions can move freely, so they can carry current. I don't need to mention the carrying current again. I've already received my mark for that. But yeah, the ions can move freely, so then can carry current in liquid form. What's an electrolyte? It's an ionic compound with free moving ions that can conduct electricity. Again, don't just say free ions. Free moving, that can conduct electricity. And if I look here at my examples, sodium chloride, it's ionic, it's aqueous, The ions move freely, it is an electrolyte. Lead bromide, it's ionic, but it's solid, those ions don't move freely, not an electrolyte. Potassium chloride liquid, ions move freely. Magnesium oxide solid, ions don't move freely. Copper sulfate solution, so again that word solution there is the same as aqueous, the ions do move freely, it is an electrolyte. If you were to split the following ionic compounds, you would get the metal and the non-metal. Pay attention to the name of the non-metal, it should end in INE, not IDE. So in the next video we are going to look at exactly how electrolysis works and predicting the products at the cathode and the anode when you've got molten ionic compounds and when you have got aqueous ionic compounds.